Hey everyone, and welcome to our first dive into mechanics. Let me ask you something. What does it cost to make a tiny math mistake? Sometimes, not much, but in 1999, it cost NASA $125 million. That's right. They launched the Mars Climate Orbiter, a marvel of engineering, and it went all the way to Mars, only to crash and burn. Why? Because one team of brilliant engineers was doing their calculations in meters, while another team was using feet. This simple mix-up sent the orbiter on a collision course. It's a jaw-dropping, real-life example of why our topic today is so critical. In physics, a number without a unit isn't just a small mistake. It can be a full-blown disaster. So welcome to the very first and most fundamental step of our mechanics course, units and measurement. So what exactly are we talking about here? In physics, our job is to describe the universe. We do that using quantities, things we can measure. But if I just walked up to you and said, hey, I'm 5 tall, what would that even mean? Am I 5 feet tall? 5 meters? Maybe I'm an action figure and I'm 5 centimeters tall. Without a unit, the number 5 is completely useless. Units provide the crucial context that gives numbers their meaning. They are the universal language that scientists all across the globe use to communicate precisely and avoid, crashing spaceships into planets. To make sure we're all speaking the same language, scientists came together and created a standardized system. It's called the International System of Units, or SI for short. You might know it as the metric system. For our journey into mechanics, we're going to start by focusing on what I call the big 3 fundamental units. These are the building blocks for almost everything else we'll encounter. First up is length, which we measure in meters. The symbol for that is a lowercase m. Second is mass, which we measure in kilograms, symbolized by kg. And third is time, which we measure in seconds with the symbol s. Think of these 3, meters, kilograms, and seconds, as the primary colors of mechanics. Almost every other unit we'll use, like force, energy, momentum, or pressure, is just a combination of these 3, mixed and matched in different ways. They are the absolute foundation. Now, one of the coolest and most mind-bending things about physics is the incredible range of scales we work with. We talk about things that are astronomically massive and things that are unimaginably microscopic. For example, the mass of the Earth is about 6 septillion kilograms. That's a 6 followed by 24 zeros. Writing that out every time would be a nightmare, and it's super easy to miss a zero and throw off your entire calculation. On the other end of the spectrum, the diameter of a single hydrogen atom is about 1/10 billionth of a meter. That's a decimal point followed by 9 zeros, and then a 1. Again, just try writing that without making a mistake. To save our sanity and prevent these kinds of errors, we use a powerful tool called scientific notation. It's a way to write very large or very small numbers compactly. Instead of writing out a million, which is a 1 with 6 zeros, we simply write 10 to the power of 6. We can write 1 times 10 to the power of minus 10 meters. It's clean, it's efficient, and it dramatically reduces the chances of making a simple but costly mistake. This is one of the first mathematical skills you absolutely need to master for physics, and we'll be using it constantly. But there's another layer to this that makes the metric system so elegant: prefixes. You've heard of these before, even if you don't think about them. Kilo literally means 1,000, so a kilogram is 1,000 grams. A kilometer is 1,000 meters. Milli, on the other hand, means 1,000th. So a millimeter is 1,000th of a meter. And it doesn't stop there. We have giga for a billion, mega for a million, micro for a millionth, and nano for a billionth. This prefix system allows us to seamlessly scale our measurements up or down. Whether we are measuring the vast distances between galaxies in gigameters or the width of a human hair in micrometers, the metric system scales perfectly and logically by simple factors of 10. This makes conversions incredibly straightforward, unlike systems where you have to remember things like 12 inches in a foot and 5,280 feet in a mile. So why are we spending so much time on this? Because mastering units is like learning the alphabet before you try to write a novel. It's the absolute non-negotiable first step. If your units are wrong, your answer will be wrong. no matter how perfectly you execute the rest of the physics. It's the first thing you should check when you solve a problem, and the last thing you should confirm before you finalize an answer. Once you become fluent in this language of measurement, once meters, kilograms, seconds, and scientific notation become second nature, you'll be ready to start describing the world in motion. And that brings us to what's next. In our next video, we're going to unlock a technique that feels like a cheat code for physics. It's called dimensional analysis. It is a powerful method that uses the units themselves to check if your equations are even possible. It can help you catch mistakes before they happen, and even help you figure out the form of an equation if you've forgotten it. It's an indispensable tool in any physicist's toolkit. This journey through the laws of the universe is just beginning, and I'm thrilled to have you here with me. If you found this helpful, don't forget to hit that like button and subscribe so you don't miss the next lesson. Thanks for watching, and I'll see you in the next video.